Hello, and welcome to Calm Science Nights. I'm so glad you're here with me tonight. Before we begin our peaceful journey through the nature of time, if you find comfort in drifting off to the soothing rhythm of temporal mysteries, please consider subscribing to the channel. It helps us create more of these tranquil explorations together. Now, settle into your most comfortable position. Let the weight of the day lift from your shoulders. Tonight, we're going to explore one of the universe's deepest mysteries, time itself. What is time? Why does it flow in only one direction? Does it really flow at all, or is that an illusion? Over the next 100 facts, we'll trace humanity's journey to understand this elusive dimension, from ancient sundials to Einstein's relativity, from quantum mechanics to the arrow of time. There's no need to remember everything tonight. In fact, there's no need to stay awake at all. Let these words wash over you like gentle waves, each fact a soft ripple in the stream of understanding, carrying you peacefully towards sleep. Just allow the story to unfold at its own unhurried pace, the way time itself seems to flow, steadily, inevitably, always forward, never back. Close your eyes now, and feel the passing of time. Feel your breath moving in and out, the gentle rhythm of your heartbeat, the quiet progression from one moment to the next. Time is the most familiar thing in our experience. We live within it every second of our lives, yet it's also the most mysterious. We can measure it, track it, even try to save it or waste it, but we can't quite say what it is. Our story begins in the ancient world, where humans first tried to make sense of time's passage. For our earliest ancestors, time was marked by the rhythms of nature, the cycle of day and night, the phases of the moon, the progression of seasons. The sun rose and set with perfect regularity. The moon waxed and waned in its monthly cycle. Winter gave way to spring, spring to summer, summer to autumn, and autumn back to winter in an endless circle. These natural cycles provided the first clocks, the first calendars, the first ways of organizing and measuring the flow of time. The ancient Egyptians, living along the Nile River around 3000 BCE, were among the first to develop sophisticated timekeeping. They noticed that certain stars appear on the horizon just before sunrise at specific times of the year, a phenomenon called heliacal rising. The star Sirius, the brightest star in the night sky, had a particularly important heliacal rising that coincided with the annual flooding of the Nile, an event crucial to Egyptian agriculture. By tracking the movements of stars, the Egyptians created one of the first accurate calendars, dividing the year into 12 months of 30 days each, plus 5 extra days, giving them a 365-day year remarkably close to the true solar year. But the Egyptians also needed to measure time within a single day, not just across the year. For this, they invented the sundial, one of humanity's first timekeeping instruments. A sundial consists of a flat surface marked with lines and a raised piece called a gnomon that casts a shadow. As the sun moves across the sky, the shadow moves across the marked surface, indicating the time of day. The Egyptians divided daylight into 12 hours, though these hours were not equal to our modern hours. They varied in length depending on the season, longer in summer when days were long, shorter in winter when days were short. This system of variable hours might seem strange to us now, but it made sense in a world where timekeeping was tied directly to the sun's position. The concept of fixed, equal hours, hours that are the same length regardless of the season or time of day, would come much later. For the ancients, time was flexible, changing with the seasons, intimately connected to the natural world. The ancient Greeks inherited much of their astronomical and timekeeping knowledge from the Egyptians and Babylonians, but they added something new: philosophical inquiry into the nature of time itself. The pre-Socratic philosopher Heraclitus, living around 500 BCE, famously declared that you cannot step into the same river twice, emphasizing the constant flow and change of all things. Time, for Heraclitus, was characterized by perpetual flux. Everything is always changing, always flowing, always becoming something other than what it was. Other Greek philosophers took different views. Parmenides, a contemporary of Heraclitus, argued the opposite, that change is an illusion and that reality is eternal and unchanging. According to Parmenides, the appearance of time and change is merely a deception of our senses. True reality is timeless and static. This tension between time as real and fundamental versus time as illusory would echo through philosophy and physics for the next 2,500 years. Aristotle, perhaps the most influential of the ancient Greek philosophers, offered a more nuanced view of time in his work Physics, written around 350 BCE. He defined time as the number of motion with respect to before and after. In other words, time is what we use to measure change and motion. Without change, without things moving from one state to another, there would be no time. Time, for Aristotle, is not something independent that exists on its own, but rather a way of measuring and understanding the changes that occur in the physical world. Aristotle also grappled with puzzling questions about time that remain relevant today. He asked, does time require a mind to measure it, or does it exist independently of observers? Can time exist without change? What about the past and future? Do they exist in the same way the present does? The past is gone, no longer existing. The future hasn't happened yet, so it doesn't exist either. That leaves only the present moment, but the present is infinitesimally brief, constantly slipping from future into past. So in what sense does time exist at all? These questions troubled Aristotle, and he didn't fully resolve them. But his willingness to ask them, to probe the conceptual difficulties surrounding time, established a tradition of deep thinking about temporality that would continue through the ages. His definition of time as the measure of change would influence thinkers for centuries, though it would eventually be challenged and refined as human understanding of physics evolved. Beyond philosophy, the ancient world also saw practical developments in timekeeping. The Greeks and Romans developed water clocks, called clepsydry, which measured time by the regulated flow of water from one container to another. Unlike sundials, water clocks could work at night or on cloudy days, making them more versatile. Elaborate water clocks were constructed with gears and mechanisms to mark the hours, some even including automated figures or sounds to announce the passage of time. These devices represented a significant step toward mechanical timekeeping, toward measuring time independently of the sun's position. But all these ancient methods of measuring time shared a common limitation. They could only measure the passage of time relative to natural phenomena, the sun's movement, water flowing, sand falling through an hourglass. They couldn't answer the deeper question of what time actually is. Is it a substance? A dimension? A fundamental feature of reality? Or is it something our minds impose on a timeless universe to make sense of change and motion? The Roman philosopher Augustine of Hippo, writing around 400 CE, captured the profound mystery of time in a famous passage. What then is time? If no one asks me, I know what it is. If I wish to explain it to him who asks, I know not. Augustine recognized that time is something we intuitively understand through our lived experience. We know what it means for time to pass, for one event to happen before another, for the future to become the present and the present to become the past. Yet when we try to define time precisely, to explain what it actually is, we find ourselves in deep conceptual waters. And so our journey has begun with the ancient world's attempts to understand and measure time, starting with the natural rhythms that governed human life. We learn that our earliest ancestors marked time by nature's cycles, the daily rising and setting of the sun, the monthly waxing and waning of the moon, the yearly progression of seasons. These natural cycles provided the first clocks and calendars, the first ways of organizing time's flow. We discovered the ancient Egyptians around 3000 BCE were among first to develop sophisticated timekeeping, noticing that certain stars appear on the horizon just before sunrise at specific times of year, heliacal rising. The star Sirius had particularly important heliacal rising coinciding with annual Nile flooding crucial to Egyptian agriculture. By tracking star movements, Egyptians created one of first accurate calendars, dividing year into 12 months of 30 days each plus 5 extra days, giving 365-day year remarkably close to true solar year. We found Egyptians also needed to measure time within single day, for this invented the sundial, one of humanity's first timekeeping instruments consisting of flat surface marked with lines and raised piece, gnomon, casting shadow. As sun moves across sky, shadow moves across marked surface indicating time of day. Egyptians divided daylight into 12 hours, though these hours were not equal to our modern hours, varied in length depending on season, longer in summer when days long, shorter in winter when days short. We learned this system of variable hours might seem strange now but made sense in a world where timekeeping tied directly to sun's position. Concept of fixed equal hours, same length regardless of season or time of day, would come much later. For ancients, time was flexible, changing with seasons, intimately connected to natural world. We discovered ancient Greeks inherited astronomical and timekeeping knowledge from Egyptians and Babylonians but added something new, philosophical inquiry into time's nature itself. Pre-Socratic philosopher Heraclitus, living around 500 BCE, famously declared, "You cannot step into the same river twice," emphasizing constant flow and change of all things. Time for Heraclitus characterized by perpetual flux, everything always changing, flowing, becoming something other than what it was. We met other Greek philosophers taking different views. Parmenides, Heraclitus' contemporary, argued opposite. Change is illusion and reality is eternal and unchanging. According to Parmenides, time and change appearance is merely sense deception. True reality is timeless and static. This tension between time as real and fundamental versus time as illusory would echo through philosophy and physics for next 2,500 years. We found Aristotle, perhaps most influential ancient Greek philosopher, offered more nuanced time view in his work Physics, written around 350 BCE. Defined time as the number of motion with respect to before and after. In other words, time is what we use to measure change and motion. Without change, without things moving from one state to another, there would be no time. Time for Aristotle not something independent existing on its own, but rather way of measuring and understanding changes occurring in physical world. We learned Aristotle also grappled with puzzling time questions remaining relevant today. Does time require mind to measure it or exist independently of observers? Can time exist without change? What about past and future? Do they exist same way present does? Past is gone, no longer existing. Future hasn't happened yet, so doesn't exist either. Leaves only present moment, but present infinitesimally brief, constantly slipping from future into past. So in what sense does time exist at all? We discovered these questions troubled Aristotle, and he didn't fully resolve them, but willingness to ask them, to probe conceptual difficulties surrounding time, established tradition of deep thinking about temporality continuing through ages. His definition of time as measure of change would influence thinkers for centuries, though eventually challenged and refined as human physics understanding evolved. We found beyond philosophy, ancient worlds saw practical timekeeping developments. Greeks and Romans developed water clocks, clepsydry, measuring time by regulated water flow from one container to another. Unlike sundials, water clocks could work at night or on cloudy days, making them more versatile. Elaborate water clocks constructed with gears and mechanisms to mark hours, some including automated figures or sounds to announce time passage, represented significant step toward mechanical timekeeping, toward measuring time independently of sun's position. We learned all these ancient time-measuring methods shared common limitation, could only measure time passage relative to natural phenomena, sun's movement, water flowing, sand falling through hourglass. Couldn't answer deeper question of what time actually is: substance, dimension, fundamental reality feature, or something our minds impose on timeless universe to make sense of change and motion. We met Roman philosopher Augustine of Hippo writing around 400 CE, who captured profound time mystery and famous passage, "What then is time? If no one asks me, I know what it is. If I wish to explain it to him who asks, I know not." Augustine recognized time as something we intuitively understand through lived experience, know what it means for time to pass, for one event to happen before another, for future to become present and present to become past. Yet when we try to define time precisely, to explain what it actually is, we find ourselves in deep conceptual waters. Each fact a gentle step in understanding's slow emergence, the gradual realization that time is both the most familiar and most mysterious aspect of our existence. From Egyptian stargazers to Greek philosophers, from sundials to water clocks, from Heraclitus's river to Augustine's confession of ignorance, humanity has always been fascinated by time, always trying to grasp something that slips through our fingers like water. Feel yourself in that ancient wondering now, standing with those first timekeepers, watching shadows move across sundials, watching water drip steadily from one vessel to another, asking the same questions we still ask today. What is time? Why does it flow? Can we ever truly understand it? There's nothing to solve tonight, nothing to grasp. Just rest in the gentle mystery of time's passage, in the peaceful rhythm of moments flowing one into another, like the water in an ancient clepsydra, steady and unhurried. Let time carry you now, that invisible current moving always forward, carrying you from waking into sleep, from one moment to the next, peaceful and inevitable, drifting gently toward rest. As we continue our peaceful journey through the story of time, we move forward from the ancient world into the medieval and early modern periods, where mechanical ingenuity would transform timekeeping and where the first hints of time's true nature would begin to emerge. The questions that troubled Aristotle and Augustine would not be answered for many centuries, but each generation would add new layers of understanding, new ways of measuring and thinking about this elusive dimension. The development of mechanical clocks in medieval Europe represented a revolution in how humans measured and experienced time. The exact origins of the mechanical clock are somewhat obscure, lost in the mists of history, but by the late 13th century, large mechanical clocks began appearing in churches and town squares across Europe. These early clocks used a mechanism called an escapement, a device that allowed a weight or spring to release energy in regular, controlled pulses, creating the steady tick-tock rhythm we associate with clocks. The escapement was a brilliant invention, perhaps one of the most important in the history of timekeeping. Before the escapement, there was no reliable way to convert the continuous force of a falling weight or unwinding spring into the regular, periodic motion needed to measure time accurately. The escapement solved this problem through an ingenious mechanism. A toothed wheel would be allowed to advance by exactly one tooth at regular intervals, controlled by an oscillating mechanism such as a foliot, a horizontal bar with weights on each end that would swing back and forth. These early mechanical clocks were not particularly accurate by modern standards. They might gain or lose 15 minutes or more per day, but they represented something profoundly new. For the first time, humans had a device that could measure time mechanically, independent of the sun, the stars, or flowing water. Time was being abstracted from nature, turned into something that could be divided into equal, consistent units regardless of the season or weather. This was when the modern concept of the hour as a fixed unit, 60 minutes, each containing 60 seconds, began to solidify. The spread of mechanical clocks through European cities in the 14th and 15th centuries had social and psychological effects that went far beyond simply telling time more accurately. The regular tolling of church bells marking the hours began to structure daily life in new ways. Work, prayer, meals, and sleep became increasingly regulated by the clock rather than by natural rhythms. Time became something to be measured, managed, and even saved or wasted, concepts that would have been strange to earlier societies where time was experienced more organically, flowing with the rhythms of day and night, season and harvest. The invention of the pendulum clock in the 17th century brought a dramatic improvement in accuracy. Galileo Galilei, the same scientist who had turned his telescope to the heavens and discovered the moons of Jupiter, also made a crucial observation about pendulums around 1602. He noticed that a pendulum takes the same amount of time to complete one swing regardless of how far it swings, a property called isochronism. A pendulum swinging through a large arc takes the same time to complete its swing as one swinging through a small arc, at least approximately. This remarkable property made pendulums ideal for regulating clocks. Galileo designed a pendulum clock late in his life, but he died before it could be built. The first working pendulum clock was constructed in 1656 by the Dutch scientist Christian Huygens, who also made important contributions to astronomy and optics. Huygens's pendulum clock was far more accurate than any previous timekeeper, losing or gaining only about 15 seconds per day rather than 15 minutes. This improvement was revolutionary. Suddenly, time could be measured with precision that had never before been possible. The accuracy of pendulum clocks improved further over the following century as craftsmen refined the design. By the 18th century, the best pendulum clocks, often called regulators, could keep time to within a second per day or better. This level of precision was crucial for scientific work and for practical applications like navigation. Accurate timekeeping at sea became essential for determining longitude, a ship's east-west position, which required comparing local time, determined by the sun's position, with the time at a reference location like Greenwich, England. This problem of determining longitude at sea led to one of the great technological challenges of the 18th century, ultimately solved by John Harrison, an English clockmaker who spent decades perfecting marine chronometers, clocks accurate enough to keep time reliably on a rolling ship for months at a time. Harrison's H4 chronometer, completed in 1759, was so accurate that it lost only 5 seconds during an 81-day voyage across the Atlantic Ocean. This achievement transformed navigation and made long-distance sea travel far safer and more reliable. But even as clockmakers were perfecting mechanical timekeeping, philosophers and scientists were beginning to ask deeper questions about the nature of time itself. Isaac Newton, whose laws of motion and universal gravitation revolutionized physics in the late 17th century, also proposed a particular view of time that would dominate scientific thinking for more than 2 centuries. In his masterwork Philosophiae Naturalis Principia Mathematica, published in 1687, Newton distinguished between absolute time and relative time. Absolute time, according to Newton, flows uniformly throughout the universe, completely independent of anything happening in it. Absolute, true, and mathematical time, of itself, and from its own nature, flows equably without relation to anything external, Newton wrote. This absolute time was like an invisible river flowing steadily through the cosmos, the same everywhere and everywhen, providing a universal framework against which all motion and change could be measured. Events could be said to happen at a particular moment in absolute time, and different observers, no matter where they were or how they were moving, would agree on when things happened and how much time elapsed between events. Relative time, on the other hand, was the time we actually measure with clocks, the apparent, sensible measure of duration based on the motion of objects. The time shown by sundials, water clocks, or mechanical clocks was relative time, an approximation or measure of true absolute time. For Newton, absolute time was the fundamental reality, while relative time was merely our practical way of accessing it. Newton's contemporary and intellectual rival, Gottfried Wilhelm Leibniz, disagreed fundamentally with this view. Leibniz argued that time was not an independent substance or container but rather a relationship between events. Time, for Leibniz, was the order of succession. It existed because events happened in sequence, one after another, and our concept of time was just a way of organizing and understanding these sequences. Without events, without change, there would be no time. This was a relational view of time, in contrast to Newton's absolute, substantival view. The debate between Newton and Leibniz about the nature of time and space, conducted partly through letters and partly through representatives, was one of the great intellectual disputes of the early modern period. The exchange, known as the Leibniz-Clarke correspondence, Clarke being Samuel Clarke, who defended Newton's views, touched on deep metaphysical questions. If time is absolute, existing independently of events, then what does it mean for time to exist? Before the creation of the universe, or in a region of space where nothing is happening? Leibniz found such ideas incoherent, while Newtonians insisted that the mathematical success of Newton's physics demonstrated that absolute time must be real. And so we moved from the ancient world into medieval and early modern periods where mechanical ingenuity transformed timekeeping and first hints of time's true nature began emerging. Questions troubling Aristotle and Augustine wouldn't be answered for many centuries, but each generation added new understanding layers, new ways of measuring and thinking about this elusive dimension. We learned mechanical clock development in medieval Europe represented revolution in how humans measured and experienced time. Exact origins somewhat obscure, lost in history's mists, but by late 13th century large mechanical clocks began appearing in European churches and town squares. These early clocks used mechanism called escapement, device allowing weight or spring to release energy in regular controlled pulses, creating steady tick-tock rhythm we associate with clocks. We discovered escapement was brilliant invention, perhaps one of most important in timekeeping history. Before escapement, no reliable way to convert continuous falling weight or unwinding spring force into regular periodic motion needed to measure time accurately. Escapement solved this through ingenious mechanism. Toothed wheel allowed to advance by exactly one tooth at regular intervals, controlled by oscillating mechanisms such as foliate, horizontal bar with weights on each end swinging back and forth. We found early mechanical clocks, not particularly accurate by modern standards, might gain or lose 15+ minutes per day, but represented something profoundly new. First time humans had device measuring time mechanically independent of sun, stars, or flowing water. Time being abstracted from nature, turned into something divisible into equal consistent units regardless of season or weather. When modern hour concept as fixed unit, 60 minutes each containing 60 seconds, began solidifying. We learned mechanical clocks spread through 14th to 15th century European cities had social and psychological effects beyond simply telling time more accurately. Regular church bell tolling marking hours began structuring daily life in new ways. Work, prayer, meals, sleep became increasingly clock-regulated rather than by natural rhythms. Time became something to be measured, managed, even saved or wasted, concepts strange to earlier societies where time experienced more organically flowing with day-night rhythms, season and harvest. We discovered pendulum clock invention in 17th century brought dramatic accuracy improvement. Galileo Galilei, same scientist who turned telescope to heavens discovering Jupiter's moons, also made crucial pendulum observation around 1602, noticed pendulum takes same time to complete one swing regardless of how far it swings, property called isochronism. Pendulum swinging through large arc takes same time as one swinging through small arc at least approximately. Remarkable property made pendulums ideal for regulating clocks. We found Galileo designed pendulum clock late in life but died before it could be built. First working pendulum clock constructed 1656 by Dutch scientist Christian Huygens, also made important astronomy and optics contributions. Huygens' pendulum clock far more accurate than any previous timekeeper, losing or gaining only about 15 seconds per day rather than 15 minutes. Revolutionary improvement. Suddenly time could be measured with never before possible precision. We learned pendulum clock accuracy improved further over following century as craftsmen refined design. By 18th century best pendulum clocks, often called regulators, could keep time to within second per day or better. This precision level crucial for scientific work and practical applications like navigation. Accurate timekeeping at sea became essential for determining longitude, ship's east-west position, requiring comparing local time, determined by sun's position, with time at reference location like Greenwich, England. We discovered longitude problem led to great 18th century technological challenge ultimately solved by John Harrison, English clockmaker who spent decades perfecting marine chronometers, clocks accurate enough to keep time reliably on rolling ship for months. Harrison's H4 chronometer completed 1759 was so accurate lost only 5 seconds during 81-day Atlantic Ocean voyage. Achievement transformed navigation, making long-distance sea travel far safer and more reliable. We found even as clockmakers perfecting mechanical timekeeping, philosophers and scientists beginning to ask deeper time-nature questions. Isaac Newton, whose motion laws and universal gravitation revolutionized late 17th century physics, also proposed particular time view dominating scientific thinking for 200+ years. In masterwork Philosophiae Naturalis Principia Mathematica, published 1687, Newton distinguished between absolute time and relative time. We learned absolute time, according to Newton, flows uniformly throughout universe, completely independent of anything happening in it, absolute, true, and mathematical time, of itself, and from its own nature, flows equably without relation to anything external, Newton wrote. This absolute time, like invisible river flowing steadily through cosmos, same everywhere and everywhen, providing universal framework against which all motion and change could be measured. Events could happen at particular moment in absolute time. Different observers, no matter where or how moving, would agree on when things happened and how much time elapsed between events. We discovered relative time, on other hand, was time we actually measure with clocks, apparent sensible measure of duration based on object motion. Time shown by sundials, water clocks, or mechanical clocks was relative time, approximation or measure of true absolute time. For Newton, absolute time was fundamental reality, while relative time merely our practical way of accessing it. We met Newton's contemporary and intellectual rival Gottfried Wilhelm Leibniz, who disagreed fundamentally with this view. Leibniz argued time was not independent substance or container, but rather relationship between events. Time for Leibniz was order of succession, existed because events happened in sequence one after another. Our time concept just way of organizing and understanding these sequences. Without events, without change, there would be no time. This was relational time view in contrast to Newton's absolute substantival view. We learned debate between Newton and Leibniz about time and space nature, conducted partly through letters, partly through representatives, was one of early modern period's great intellectual disputes, exchange known as Leibniz-Clarke correspondence, Clarke being Samuel Clarke defending Newton's views, touched on deep metaphysical questions. If time is absolute, existing independently of events, what does it mean for time to exist before universe creation or in space region where nothing happening? Leibniz found such ideas incoherent, while Newtonians insisted Newton's physics mathematical success demonstrated absolute time must be real. Each fact a gentle step in understanding's evolution, the gradual transformation from ancient sundials to precise mechanical clocks, from measuring time's passage to debating its fundamental nature. Escapements allowing regular ticking, pendulums swinging isochronously, Harrison's chronometer keeping time across rolling Atlantic seas, Newton proposing absolute time flowing like invisible universal river, Leibniz arguing time is merely the order of succession. Rest in this slow accumulation of knowledge now, this recognition that humans have always been refining their understanding of time, always trying to measure it more precisely, always asking what it truly is. The tick of a clock, the swing of a pendulum, the steady flow Newton imagined, all attempts to grasp something that remains elusive. Let yourself drift with time's patient progression, that steady advance from one moment to the next, whether absolute river or relational sequence, peaceful and unhurried, carried gently towards sleep. As we continue our peaceful journey through the story of time, we move from the age of Newton and mechanical clocks into the 19th and early 20th centuries, when the nature of time would be questioned and ultimately transformed in ways that Newton could never have imagined. The absolute time that seemed so certain, so fundamental to physics, would turn out to be an approximation, the useful fiction that works well in everyday life but breaks down when we examine the universe at its extremes. For nearly 200 years after Newton published the Principia, his vision of absolute time reigned supreme in physics. Scientists used Newtonian mechanics to calculate planetary orbits, predict eclipses, and understand the motion of everything from falling apples to spinning galaxies. And it all worked beautifully. Newton's laws, operating within the framework of absolute time and absolute space, seemed to describe the universe with perfect accuracy. Time was the unchanging stage on which the drama of physics played out, the same for everyone everywhere. But in the 19th century, physicists studying light and electricity began to notice something puzzling. Light, they discovered, was an electromagnetic wave, a rippling disturbance in electric and magnetic fields that propagated through space at a specific speed. The Scottish physicist James Clerk Maxwell, working in the 1860s, unified the theories of electricity and magnetism into a single elegant framework described by a set of equations that now bear his name. Maxwell's equations predicted that electromagnetic waves would travel at a specific speed, approximately 300,000 kilometers per second, or about 186,000 miles per second. This prediction matched perfectly with measurements of the speed of light, revealing that light itself was an electromagnetic wave. But there was something strange about Maxwell's equations. Unlike the equations describing sound waves, which travel at different speeds depending on whether you're moving toward or away from the source, Maxwell's equations seemed to predict that light would always travel at the same speed, regardless of the motion of the source or the observer. This didn't make intuitive sense. If you're driving toward a sound source, you encounter the sound waves more quickly, so sound travels faster relative to you. Shouldn't the same be true for light? This puzzle led physicists to propose the existence of a luminiferous ether, an invisible medium filling all of space through which light waves propagated, just as sound waves propagate through air or water waves through water. If such an ether existed, then Maxwell's equations would describe the speed of light relative to this ether, and observers moving through the ether would measure different speeds for light depending on their motion, just as Newton's absolute space would predict. In 1887, two American physicists, Albert Michelson and Edward Morley, conducted what would become one of the most famous experiments in the history of physics. They built an extremely sensitive device called an interferometer designed to detect Earth's motion through the supposed ether. The reasoning was simple: as Earth orbits the Sun, it must be moving through the ether at different speeds at different times of year. This motion should create an ether wind, a detectable difference in the speed of light measured in different directions, just as a person walking through still air would experience wind. Michelson and Morley's experiment was brilliantly designed and executed with extraordinary precision. They split a beam of light into two perpendicular paths, sent the beams on journeys of equal length, then recombined them. If Earth were moving through the ether, light traveling along the direction of Earth's motion should take slightly longer, fighting against the ether wind one way and being helped by it on the return, than light traveling perpendicular to Earth's motion. This tiny difference would show up as a shift in the interference pattern when the beams recombined. The experiment was repeated many times, at different times of day and different times of year, with ever-increasing precision. The result was always the same, no difference. No ether wind. The speed of light appeared to be exactly the same in all directions, regardless of Earth's motion. This was shocking and deeply puzzling. If there was no detectable ether wind, did that mean Earth was somehow stationary in the ether, or returned to pre-Copernican ideas of Earth being at the center of everything? That seemed impossible. But if Earth was moving through the ether, why couldn't the experiment detect it? Various explanations were proposed to explain this null result, but they all seemed contrived or incomplete. The Dutch physicist Hendrik Lorentz and the Irish physicist George Fitzgerald independently suggested that objects might physically contract in the direction of motion through the ether by just the right amount to cancel out the expected effect, but this seemed like an ad hoc fix rather than a genuine explanation. The physics community was in a state of confusion and uncertainty. Something fundamental about space, time, or light wasn't behaving as expected. The resolution to this puzzle came in 1905 from an unexpected source, a 26-year-old patent clerk in Bern, Switzerland, named Albert Einstein. In a paper titled On the Electrodynamics of Moving Bodies, Einstein proposed something radical. Perhaps the problem wasn't with the experiment or with the ether, but with our fundamental assumptions about space and time. Einstein began with two simple postulates. First, that the laws of physics are the same in all inertial reference frames moving at constant velocity, and second, that the speed of light in vacuum is the same for all observers, regardless of their motion or the motion of the light source. This second postulate was the revolutionary one. It meant taking Maxwell's equations at face value. The speed of light really is constant, not relative to some ether, but as an absolute feature of the universe. But if the speed of light is the same for all observers, something else must give. If you're standing still and measure light traveling at 300,000 kilometers per second, and I'm moving toward the light source at half the speed of light and also measure light traveling at 300,000 kilometers per second, then our measurements of distance and time must be different. We can't both measure the same speed for light unless we disagree about how far the light traveled and how long it took. This realization led Einstein to a profound conclusion: time is not absolute. Two observers in relative motion will not agree on the duration between events or even on whether two events are simultaneous. This phenomenon is called time dilation. If you're moving relative to me at a significant fraction of the speed of light, I will observe that your clocks are running slow compared to mine. You, from your perspective, will see my clocks running slow compared to yours. Neither of us is wrong. Time genuinely passes at different rates in different reference frames. Einstein illustrated this with thought experiments, the most famous involving light clocks, imaginary clocks that measure time by bouncing a pulse of light between two mirrors. If such a clock is moving relative to you, the light pulse appears to travel a longer diagonal path, from your perspective, as the clock moves, so it takes longer for the light to make each round trip. Since the speed of light is constant, the moving clock must tick more slowly. This is not an illusion or a measurement error. Time itself is genuinely passing more slowly for the moving clock. The equations Einstein derived, now called the Lorentz transformations, building on Lorenz's earlier mathematical work but giving them a completely new physical interpretation, precisely described how time and space measurements change between different reference frames. These transformations showed that time dilation increases with velocity. At everyday speeds, the effect is immeasurably tiny. A person in a car moving at highway speeds ages about 1 nanosecond less per hour of driving than someone standing still. But at speeds approaching the speed of light, the effect becomes dramatic. At 90% of light speed, time passes at only about 44% of its normal rate. At 99.9% of light speed, time slows to about 4.5% of normal. And so we learn for nearly 200 years after Newton published Principia his absolute time vision reigned supreme in physics. Scientists used Newtonian mechanics to calculate planetary orbits, predict eclipses, understand motion from falling apples to spinning galaxies, and it all worked beautifully. Newton's laws operating within absolute time and space frameworks seem to describe universe with perfect accuracy. Time was unchanging stage on which physics drama played out, same for everyone everywhere. We discovered, but in 19th century physicists studying light and electricity began noticing something puzzling. Light they found was electromagnetic wave, rippling disturbance in electric and magnetic fields propagating through space at specific speed. Scottish physicist James Clerk Maxwell, working in 1860s, unified electricity and magnetism theories into single elegant framework described by equations now bearing his name. Maxwell's equations predicted electromagnetic waves would travel at specific speed, approximately 300,000 kilometers per second or about 186,000 miles per second. We found prediction matched perfectly with light speed measurements revealing light itself was electromagnetic wave, but something strange about Maxwell's equations, unlike equations describing sound waves, traveling at different speeds depending on whether moving toward or away from source, Maxwell's equations seemed to predict light would always travel at same speed regardless of source or observer motion. Didn't make intuitive sense. If driving towards sound source encounters sound waves more quickly so sound travels faster relative to you, shouldn't same be true for light? We learned puzzle led physicists to propose luminiferous ether existence, invisible medium filling all space through which light waves propagated just as sound waves propagate through air or water waves through water. If such ether existed, then Maxwell's equations would describe light speed relative to this ether, and observers moving through ether would measure different light speeds depending on their motion, just as Newton's absolute space would predict. We discovered in 1887 two American physicists Albert Michelson and Edward Morley conducted what would become one of physics history's most famous experiments, built extremely sensitive device called interferometer designed to detect Earth's motion through supposed ether. Reasoning simple, as Earth orbits Sun must be moving through ether at different speeds at different year times. This motion should create ether wind, detectable difference in light speed measured in different directions, just as person walking through still air would experience wind. We found Michelson and Morley's experiment brilliantly designed and executed with extraordinary precision, split light beam into two perpendicular paths, sent beams on equal length journeys, then recombined them. If Earth moving through ether, light traveling along Earth's motion direction should take slightly longer, fighting ether wind one way, helped by it on return, then light traveling perpendicular to Earth's motion. Tiny difference would show as interference pattern shift when beams recombined. We learned experiment repeated many times at different day times and year times with ever-increasing precision. Result always same, no difference, no ether wind. Light speed appeared exactly same in all directions regardless of Earth's motion, shocking and deeply puzzling. If no detectable ether wind, did that mean Earth somehow stationary in ether, returned to pre-Copernican ideas of Earth at center? Seemed impossible, but if Earth moving through ether, why couldn't experiment detect it? We discovered various explanations proposed to explain null result, but all seemed contrived or incomplete. Dutch physicist Hendrik Lorentz and Irish physicist George Fitzgerald independently suggested objects might physically contract in motion direction through ether by just right amount to cancel expected effect, but seemed ad hoc fix rather than genuine explanation. Physics community in confusion and uncertainty state something fundamental about space, time, or light wasn't behaving as expected. We met resolution coming in 1905 from unexpected source, 26-year-old patent clerk in Bern, Switzerland named Albert Einstein. In paper on the electrodynamics of moving bodies, Einstein proposed something radical. Perhaps problem wasn't with experiment or ether but with our fundamental space and time assumptions. Einstein began with two simple postulates. First, physics laws same in all inertial reference frames moving at constant velocity. Second, light speed in vacuum same for all observers regardless of their motion or light source motion. We found this second postulate was revolutionary, meant taking Maxwell's equations at face value. Light speed really is constant, not relative to some ether but as absolute universe feature. But if light speed same for all observers, something else must give. If standing still measuring light traveling at 300,000 kilometers per second and moving toward light source at half light speed also measuring light at 300,000 kilometers per second, then our distance and time measurements must be different. Can't both measure same light speed unless disagree about how far light traveled and how long it took. We learned this realization led Einstein to profound conclusion: time is not absolute. Two observers in relative motion will not agree on duration between events or even on whether two events simultaneous. Phenomenon called time dilation. If moving relative to me at significant fraction of light speed, I will observe your clocks running slow compared to mine. You from your perspective will see my clocks running slow compared to yours. Neither wrong. Time genuinely passes at different rates in different reference frames. We discovered Einstein illustrated with thought experiments, most famous involving light clocks, imaginary clocks measuring time by bouncing light pulse between two mirrors. If such clock moving relative to you, light pulse appears to travel longer diagonal path, from your perspective, as clock moves so takes longer for light to make each round trip, since light speed constant, moving clock must tick more slowly. Not illusion or measurement error, time itself genuinely passing more slowly for moving clock. We found equations Einstein derived, now called Lorentz transformations, building on Lorentz's earlier mathematical work but giving completely new physical interpretation, precisely described how time and space measurements change between different reference frames. Transformations showed time dilation increases with velocity, at everyday speeds affect immeasurably tiny. Person in car at highway speeds ages about 1 nanosecond less per hour driving than someone standing still. But at speeds approaching light speed effect becomes dramatic. At 90% light speed time passes at only about 44% normal rate. At 99.9%, light speed, time slows to about 4.5% of normal. Each fact a gentle step in understanding's revolution, the gradual realization that Newton's absolute time was not fundamental truth but approximation. Maxwell revealing light's electromagnetic nature, Michelson and Morley finding no ether wind, Einstein daring to abandon absolute time itself, showing time passes differently for different observers depending on their motion, time dilation making time relative, flexible, dependent on reference frame. Rest in this profound transformation now, this recognition that time is not the rigid universal framework Newton imagined but something more fluid, more mysterious. Time itself can slow down, speed up, depend on how you're moving. The faster you go, the slower time passes for you relative to those standing still. Let yourself drift with this relativistic understanding, this recognition that time is woven together with space, that motion through space affects passage through time, peaceful and unhurried, carried gently towards sleep by time's mysterious flow. As we continue our peaceful journey through the story of time, we move deeper into Einstein's revolutionary insights and discover that time dilation was just the beginning. Special relativity, as Einstein's 1905 theory came to be called, transformed our understanding not just of time but of the very fabric of reality itself. And yet, Einstein wasn't finished. He would spend another decade grappling with an even deeper question about the nature of time, space, and gravity. One of the most striking consequences of special relativity is the relativity of simultaneity, the realization that observers in different reference frames will not agree on whether two events happen at the same time. Imagine two lightning bolts striking the front and back of a moving train simultaneously from the perspective of someone standing on the platform. An observer on the train, moving toward one lightning strike and away from the other, will receive the light from the two strikes at different times. Since the speed of light is the same for both observers, the train passenger must conclude that the strikes did not happen simultaneously. The one toward which the train was moving happened earlier. This isn't a matter of perception or delay in signals arriving. According to relativity, there is no absolute fact about whether the lightning strikes were simultaneous. Both observers are correct from their own reference frames. The platform observer is right that they were simultaneous in their frame, and the train passenger is right that they weren't simultaneous in theirs. The universe doesn't have a preferred reference frame that determines the real order of events. Simultaneity, like time itself, is relative. This relativistic understanding of time had another profound implication. Time and space are not separate, independent entities but are intimately woven together into a single four-dimensional fabric called space-time. The mathematician Hermann Minkowski, who had been one of Einstein's teachers, developed the mathematical framework for this in 1908. Minkowski showed that special relativity could be understood geometrically. Events aren't just points in three-dimensional space happening at different times, but rather points in four-dimensional space-time, where time is treated as a fourth dimension alongside the three spatial dimensions. Henceforth, space by itself, and time by itself, are doomed to fade away into mere shadows, Minkowski declared in a famous lecture, and only a kind of union of the two will preserve an independent reality. In this space-time view, an object's trajectory through time, what we experience as the object existing at different moments, is actually a world line, a path through the four-dimensional space-time. Your entire life, from birth to death, exists as a continuous curve in space-time, with every moment of your existence represented as a point along that world line. This space-time perspective raised deep philosophical questions about the nature of time and existence. If the past, present, and future all exist as different regions of space-time, then in what sense does time flow? From the space-time perspective, sometimes called the block universe view, all of time exists equally. The past hasn't gone away, and the future isn't yet to come. They're simply different regions of space-time, just as here and there are different regions of space. What we experience is the flow of time, the sense of moving from past through present to future, might be a feature of consciousness rather than a fundamental aspect of reality. While Einstein's special relativity revolutionized our understanding of time for objects moving at constant velocities, it didn't address acceleration or gravity. Einstein knew this was a limitation, and he spent the next 10 years working on a more comprehensive theory that would include these phenomena. The result, published in 1915, was general relativity, a theory that would reveal an even more profound connection between time, space, and gravity. The key insight that led Einstein to general relativity came from thinking about the equivalence between gravitational acceleration and other kinds of acceleration. Einstein realized that if you're in a closed box being accelerated through space, you can't tell the difference between that acceleration and the pull of gravity. They feel identical. Someone in a rocket accelerating at 9.8 meters per second squared would feel exactly the same force as someone standing on Earth's surface experiencing Earth's gravity. This equivalence principle, as it's called, suggested to Einstein that gravity and acceleration might be fundamentally the same phenomenon. But if gravity is equivalent to acceleration, and acceleration affects time, which it does in special relativity, accelerating clocks run slow, then gravity must also affect time. Einstein worked out the mathematics and discovered something beautiful and strange. Massive objects don't just exert a force on other objects, they warp the fabric of spacetime itself. The sun, for instance, creates a curvature in spacetime around it, and planets follow curved paths through this warped spacetime, paths that we perceive as orbits. Gravity, in Einstein's view, isn't a force at all but rather the curvature of spacetime caused by mass and energy. This curvature of spacetime has a direct effect on time. Clocks closer to a massive object, where spacetime curvature is stronger, run more slowly than clocks farther away. This phenomenon is called gravitational time dilation. On Earth's surface, time passes slightly more slowly than at high altitude. The effect is tiny. A clock at sea level runs about 10 nanoseconds per day slower than a clock on a mountaintop, but it's real and measurable. Atomic clocks are precise enough to detect this difference, and the effect must be accounted for in GPS satellites, which orbit high above Earth's surface where time passes slightly faster than on the ground. The predictions of general relativity have been tested in numerous ways over the past century, and the theory has passed every test with remarkable accuracy. One of the first confirmations came in 1919, when a solar eclipse allowed astronomers to observe stars near the sun's edge in the sky. Einstein's theory predicted that the sun's mass would curve spacetime, bending the path of light from distant stars passing near it, making the stars appear slightly displaced from their normal positions. The British astronomer Arthur Eddington led expeditions to observe the eclipse, and his measurements confirmed Einstein's prediction, making Einstein an international celebrity almost overnight. More dramatic confirmations of gravitational time dilation came from studying extreme objects like neutron stars and black holes. Near a neutron star, an object containing more than the Sun's mass compressed into a sphere only about 12 miles across, space-time is curved so severely that time passes noticeably slower than in the surrounding space. Near a black hole, the effect is even more extreme. At the event horizon of a black hole, the boundary beyond which nothing can escape, time dilation becomes infinite from the perspective of a distant observer. If you could watch someone fall toward a black hole's event horizon, you would see them slow down and appear to freeze just at the horizon, their clock appearing to stop completely, though from their own perspective they would pass through normally, time flowing as usual for them. And so we learned one of special relativity's most striking consequences is relativity of simultaneity, realization that observers in different reference frames will not agree on whether two events happen at same time. Imagine two lightning bolts striking moving trains front and back simultaneously from platform observer's perspective. Observer on train moving toward one strike and away from other receives light from two strikes at different times. Since light speed same for both observers, train passenger must conclude strikes did not happen simultaneously, one toward which train moving happened earlier. We discovered this isn't perception matter or signal arrival delay. According to relativity, no absolute fact about whether lightning strikes were simultaneous. Both observers correct from own reference frames. Platform observer right they were simultaneous in their frame. Train passenger right they weren't simultaneous in theirs. Universe doesn't have preferred reference frame determining real event order. Simultaneity, like time itself, is relative. We found relativistic time understanding had another profound implication: time and space not separate independent entities but intimately woven together into single four-dimensional fabric called space-time. Mathematician Hermann Minkowski, one of Einstein's teachers, developed mathematical framework for this in 1908, showed special relativity could be understood geometrically. Events aren't just points in three-dimensional space happening at different times but rather points in four-dimensional space-time where time treated as fourth dimension alongside three spatial dimensions. We learned henceforth space by itself, and time by itself, are doomed to fade away into mere shadows, Minkowski declared in famous lecture, and only a kind of union of the two will preserve an independent reality. In this space-time view, object's trajectory through time, what we experience as object existing at different moments, is actually world line, path through four-dimensional space-time. Your entire life from birth to death exists as continuous curve in space-time with every moment of existence represented as point along that world line. We discovered space-time perspective raised deep philosophical questions about time and existence nature. If past, present, and future all exist as different space-time regions, then in what sense does time flow? From space-time perspective, sometimes called block universe view, all of time exists equally. Past hasn't gone away, future isn't yet to come. They're simply different space-time regions, just as here and there are different space regions. What we experience as time flow, sense of moving from past through present to future, might be consciousness feature rather than fundamental reality aspect. We found while Einstein's special relativity revolutionized time understanding for constant velocity objects, didn't address acceleration or gravity, Einstein knew this was limitation, spent next 10 years working on more comprehensive theory including these phenomena. Result published 1915 was general relativity, theory revealing even more profound connection between time, space, and gravity. We learned key insight leading Einstein to general relativity came from thinking about equivalence between gravitational acceleration and other acceleration kinds. Einstein realized if enclosed box being accelerated through space can't tell difference between that acceleration and gravity pull, feel identical. Someone in rocket accelerating at 9.8 meters per second squared would feel exactly same force as someone standing on Earth's surface experiencing Earth's gravity. This equivalence principle suggested to Einstein gravity and acceleration might be fundamentally same phenomenon. We discovered but if gravity equivalent to acceleration, and acceleration affects time, which it does in special relativity, accelerating clocks run slow, then gravity must also affect time. Einstein worked out mathematics discovering something beautiful and strange. Massive objects don't just exert force on other objects, they warp space-time fabric itself. Sun, for instance, creates curvature in space-time around it. Planets follow curved paths through this warped space-time, paths we perceive as orbits. Gravity in Einstein's view isn't force at all but rather space-time curvature caused by mass and energy. We found space-time curvature has direct time effect. Clocks closer to massive object where space-time curvature stronger run more slowly than clocks farther away. Phenomenon called gravitational time dilation. On Earth's surface time passes slightly more slowly than at high altitude. Effect tiny. Clock at sea level runs about 10 nanoseconds per day slower than clock on mountaintop, but real and measurable. Atomic clocks precise enough to detect this difference. Effect must be accounted for in GPS satellites orbiting high above Earth's surface where time passes slightly faster than on ground. We learned general relativity predictions tested numerous ways over past century. Theory passed every test with remarkable accuracy. One of first confirmations came 1919 when solar eclipse allowed astronomers to observe stars near sun's edge and sky. Einstein's theory predicted sun's mass would curve spacetime bending light path from distant stars passing near it making stars appear slightly displaced from normal positions. British astronomer Arthur Eddington led expeditions to observe eclipse. Measurements confirmed Einstein's prediction, making Einstein international celebrity almost overnight. We discovered more dramatic gravitational time dilation confirmations came from studying extreme objects like neutron stars and black holes. Near neutron star, object containing more than sun's mass compressed into sphere only about 12 miles across. Space-time curved so severely time passes noticeably slower than in surrounding space. Near black hole effect even more extreme, at event horizon, boundary beyond which nothing can escape, time dilation becomes infinite from distant observer perspective. If could watch someone fall toward black hole's event horizon would see them slow down and appear to freeze just at horizon, their clock appearing to stop completely though from their own perspective would pass through normally, time flowing as usual for them. Each fact a gentle step in understanding's deepening, the gradual realization that time is woven into spacetime's fabric, that simultaneity is relative, that mass warps spacetime affecting time's passage. From Minkowski's spacetime mathematics to Einstein's general relativity, from equivalence principle to gravitational time dilation, from eclipse observations to black hole horizons, time revealed as increasingly strange and wonderful. Rest in this profound transformation now, this recognition that time near massive objects passes more slowly, that gravity is space-time curvature, that past, present, and future might all exist equally in block universe. Time is not what it seems, not the simple forward flow we experience but something far more mysterious. Let yourself drift with this warped space-time understanding, this recognition that time bends near massive objects, that your position in gravitational field affects how quickly time passes for you, peaceful and unhurried, carried gently towards sleep. As we continue our peaceful journey through the story of time, we turn from Einstein's relativity to explore another profound mystery, the arrow of time. Why does time seem to flow in only one direction? Why can we remember the past but not the future? Why do eggs break but never spontaneously reassemble? The laws of physics, as we understand them, are almost entirely time-symmetric. They work equally well whether time runs forward or backward. Yet our experience of time has a definite direction, an arrow pointing inexorably from past toward future. This puzzle of time's arrow connects deeply to the concept of entropy, a measure of disorder or randomness in a system. The second law of thermodynamics, one of the most fundamental principles in physics, states that the total entropy of an isolated system always increases over time, or at best stays the same, it never decreases. This law was formulated in the 19th century by physicists studying heat engines and energy, but its implications extend far beyond steam engines to the very nature of time itself. The Austrian physicist Ludwig Boltzmann, working in the 1870s and 1880s, provided a deeper understanding of entropy by connecting it to probability and the microscopic behavior of atoms and molecules. Boltzmann showed that entropy is essentially a measure of the number of possible microscopic arrangements that correspond to the same macroscopic state. A gas spread uniformly throughout a room has high entropy because there are many ways the individual molecules can be arranged and still produce the same overall appearance of a uniform gas. A gas confined to a small corner of the room has low entropy because there are far fewer possible molecular arrangements. The reason entropy increases, Boltzmann argued, is simply that there are vastly more high-entropy states than low-entropy states. If you release a gas from a corner of a room, it will spread out not because of any fundamental law forcing it to, but because there are so many more ways for the molecules to be spread throughout the room than concentrated in one corner. The system evolves toward higher entropy states simply because those states are overwhelmingly more probable. It's not impossible for all the air molecules in a room to spontaneously gather in one corner. It's just so fantastically unlikely that it would never happen even if you waited longer than the age of the universe. This statistical understanding of entropy provides a possible explanation for the arrow of time. If the universe began in a very low entropy state, highly ordered, with matter and energy concentrated rather than spread out, then the second law of thermodynamics guarantees that entropy will increase over time. The direction of time that we call forward is simply the direction in which entropy increases. The past is the direction of lower entropy, the future is the direction of higher entropy, and the arrow of time points from one to the other. But this explanation raises a deeper puzzle. Why did the universe begin in such a low entropy state? The Big Bang, the moment of the universe's origin about 13.8 billion years ago, was an extraordinarily special, low entropy configuration. All the matter and energy in the observable universe was concentrated in an incredibly hot, dense state. Since then, the universe has been expanding and cooling, and entropy has been steadily increasing. Stars formed and burned, scattering energy and increasing entropy. Black holes formed, which have enormous entropy. Eventually, in the far future, the universe may reach a state of maximum entropy, a heat death where all matter has decayed, All stars have burned out, and all black holes have evaporated, leaving only a thin soup of radiation in an ever-expanding space. The question of why the Big Bang had such low entropy, why the universe began in such a special, ordered state, remains one of the deepest unsolved problems in physics. Some physicists speculate that the answer might lie in quantum mechanics and the conditions that gave rise to the Big Bang itself, perhaps involving processes we don't yet understand. Others suggest that our universe might be just one of many in a vast multiverse, and the low-entropy Big Bang was simply a rare statistical fluctuation in an eternally existing cosmic landscape. But these ideas remain speculative, and the origin of time's arrow remains mysterious. The arrow of time has another puzzling aspect. It seems to emerge from time-symmetric fundamental laws. The equations of physics, whether Newton's laws, Maxwell's equations, quantum mechanics, or even Einstein's general relativity, work almost the same whether time runs forward or backward. If you filmed particles colliding and played the film backward, the reversed motion would still obey the laws of physics. The fundamental laws don't prefer one direction of time over another. Yet somehow, when we have enormous numbers of particles, when we move from the microscopic world of individual atoms to the macroscopic world of everyday objects, we get the second law of thermodynamics and the arrow of time. Order emerges from time-symmetric chaos. There's one exception to the time symmetry of fundamental physics: certain rare processes in particle physics, involving particles called kaons and B mesons, show a tiny violation of time reversal symmetry. These processes, discovered in experiments in the 1960s and later, behave slightly differently when time is reversed. However, this violation is extremely small and doesn't seem to be the origin of the macroscopic arrow of time we experience. The mystery of how the arrow of time emerges from time-symmetric, or nearly time-symmetric, fundamental laws remains one of the deepest questions in physics. Another perspective on the arrow of time comes from quantum mechanics, the theory governing the behavior of matter and energy at the smallest scales. In quantum mechanics, particles don't have definite properties until they're measured. Instead, they exist in superpositions, combinations of different possible states. When a measurement is made, the superposition collapses into one definite outcome. This measurement process, often called the collapse of the wave function, appears to be irreversible and time asymmetric. You can't unmeasure a particle and restore it to its original superposition. The physicist Roger Penrose has suggested that this quantum mechanical collapse might be related to gravity and might provide a fundamental basis for the arrow of time, though this idea remains controversial and unproven. Other interpretations of quantum mechanics, such as the many worlds interpretation, suggest that there is no true collapse. Instead, all possible measurement outcomes occur in different branches of the universe. In this view, the apparent collapse and the arrow of time might be features of our subjective experience rather than fundamental properties of reality. The connection between consciousness and time's arrow is another deep puzzle. We experience time as flowing from past to future. We remember the past but not the future. We can influence the future through our actions but can't change the past. This psychological arrow of time aligns with the thermodynamic arrow. We remember low-entropy states, the past, and not high-entropy states, the future. But why? Is our consciousness somehow fundamentally connected to the increase of entropy? Does memory depend on the thermodynamic arrow, Or could consciousness exist in a universe where entropy decreased instead of increased? Some philosophers and physicists have suggested that memory and consciousness require the increase of entropy because forming a memory involves creating a physical record, modifying the state of neurons in the brain, which necessarily increases entropy. In a hypothetical universe where entropy decreased, no stable records could be formed, and consciousness as we know it might be impossible. This would mean that the thermodynamic arrow of time doesn't just determine the direction we experience time flowing, it actually makes consciousness and memory possible in the first place. And so we turn from Einstein's relativity to explore another profound mystery, time's arrow. Why does time seem to flow in only one direction? Why can we remember past but not future? Why do eggs break but never spontaneously reassemble? Physics laws as we understand them are almost entirely time-symmetric, work equally well whether time runs forward or backward, yet our time experience has definite direction, arrow pointing inexorably from past toward future. We learn this time's arrow puzzle connects deeply to entropy concept, measure of disorder or randomness in system. Second law of thermodynamics, one of physics' most fundamental principles, states total entropy of isolated system always increases over time or at best stays same, never decreases, law formulated in 19th century by physicists studying heat engines and energy, but implications extend far beyond steam engines to time's very nature itself. We discovered Austrian physicist Ludwig Boltzmann working in 1870s to 1880s provided deeper entropy understanding by connecting it to probability and microscopic atom and molecule behavior. Boltzmann showed entropy essentially measures number of possible microscopic arrangements corresponding to same macroscopic state, gas spread uniformly throughout. Room has high entropy because many ways individual molecules can be arranged and still produce same overall uniform gas appearance. Gas confined to small room corner has low entropy because far fewer possible molecular arrangements. We found reason entropy increases, Boltzmann argued, simply that vastly more high entropy states than low entropy states exist. If release gas from room corner will spread out not because fundamental law forcing it but because so many more ways for molecules to be spread throughout room than concentrated in one corner. System evolves toward higher entropy states simply because those states overwhelmingly more probable, not impossible for all room air molecules to spontaneously gather in one corner. Just so fantastically unlikely would never happen even waiting longer than universe age. We learned statistical entropy understanding provides possible times arrow explanation. If universe began in very low entropy state, highly ordered with matter and energy concentrated rather than spread out, then second law of thermodynamics guarantees entropy will increase over time. Direction of time we call forward is simply direction in which entropy increases, past is direction of lower entropy, future is direction of higher entropy, time's arrow points from one to other. We discovered this explanation raises deeper puzzle. Why did universe begin in such low entropy state? Big Bang, universe's origin moment about 13.8 billion years ago, was extraordinarily special low entropy configuration, all observable universe matter and energy concentrated in incredibly hot dense state. Since then universe expanding and cooling, entropy steadily increasing, stars formed and burned scattering energy increasing entropy, black holes formed, have enormous entropy, eventually in far future universe may reach maximum entropy state, heat death where all matter decayed, all stars burned out, all black holes evaporated, leaving only thin radiation soup in ever-expanding space. We found question of why Big Bang had such low entropy, why universe began in such special ordered state, remains one of physics' deepest unsolved problems. Some physicists speculate answer might lie in quantum mechanics and conditions giving rise to Big Bang itself, perhaps involving processes we don't yet understand. Others suggest our universe might be just one of many in vast multiverse. Low-entropy Big Bang, simply rare statistical fluctuation in eternally existing cosmic landscape, but ideas remain speculative. Time's arrow origin remains mysterious. We learn time's arrow as another puzzling aspect, seems to emerge from time-symmetric fundamental laws. Physics equations, Newton's laws, Maxwell's equations, quantum mechanics, even Einstein's general relativity, work almost same whether time runs forward or backward. If filmed particles colliding and played film backward, reversed motion would still obey physics laws. Fundamental laws don't prefer one time direction over another. Yet somehow, when have enormous particle numbers, move from individual atom microscopic world to everyday object macroscopic world, we get second law of thermodynamics and time's arrow. Order emerges from time-symmetric chaos. We discovered one exception to fundamental physics: time symmetry. Certain rare particle physics processes involving particles called kaons and bosons showed tiny time reversal symmetry violation. Processes discovered in experiments 1960s and later behaved slightly differently when time reversed. However, violation extremely small. Doesn't seem to be macroscopic time's arrow origin we experience. Mystery of how time's arrow emerges from time-symmetric, or nearly time-symmetric, fundamental laws remains one of physics' deepest questions. We found another time's arrow perspective comes from quantum mechanics, theory governing matter and energy behavior at smallest scales. In quantum mechanics, particles don't have definite properties until measured, instead exist in superpositions, combinations of different possible states. When measurement made, superposition collapses into one definite outcome. This measurement process, often called wave function collapse, appears irreversible and time asymmetric, can't unmeasure particle and restore to original superposition. We learned physicist Roger Penrose suggested this quantum mechanical collapse might be related to gravity and might provide fundamental time's arrow basis, though idea remains controversial and unproven. Other quantum mechanics interpretations, such as many worlds interpretation, suggest no true collapse. Instead, all possible measurement outcomes occur in different universe branches. In this view, apparent collapse in time's arrow might be our subjective experience features rather than fundamental reality properties. We discovered connection between consciousness and time's arrow is another deep puzzle. We experience time as flowing from past to future, remember past but not future, can influence future through actions but can't change past. This psychological time's arrow aligns with thermodynamic arrow. We remember low entropy states / past and not high entropy states / future. But why? Is our consciousness somehow fundamentally connected to entropy increase? Does memory depend on thermodynamic arrow, or could consciousness exist in universe where entropy decreased instead of increased? We found some philosophers and physicists suggested memory and consciousness require entropy increase because forming memory involves creating physical record, modifying brain neuron state, which necessarily increases entropy. In hypothetical universe where entropy decreased, no stable records could be formed. Consciousness as we know might be impossible. would mean thermodynamic time's arrow doesn't just determine direction we experience time flowing but actually makes consciousness and memory possible in first place. Each fact a gentle step in understanding's deepening, the gradual realization that time's arrow is woven into entropy's increase, into universe's evolution from ordered Big Bang to disordered heat death. From Boltzmann's statistical mechanics to second law of thermodynamics, from low-entropy Big Bang to quantum measurement collapse, from time-symmetric laws to irreversible experience, time flows forward because entropy increases. Rest in this profound mystery now, this recognition that time's direction emerges from probability, that we remember past because it has lower entropy than future, that consciousness itself might depend on entropy's increase. Time flows like water downhill, always from order toward disorder, from concentrated to spread out, from past to future. Let yourself drift with entropy's patient increase, with time's arrow pointing always forward, with universe's slow evolution from Big Bang's ordered beginning toward heat death's disordered end, peaceful and inevitable, carried gently toward sleep. As we approach the end of our peaceful journey through the story of time, we turn to the final mysteries, what quantum mechanics tells us about time, what happens to time at the extremes of reality, and what modern physics reveals about whether time truly flows or is something more strange and subtle than we ever imagined. The questions that troubled ancient philosophers have not been fully answered, but our understanding has deepened in ways both beautiful and bewildering. In quantum mechanics, time plays a unique and somewhat paradoxical role. Unlike position, momentum, or energy, which in quantum mechanics are represented by operators and can be uncertain or exist in superposition, time is treated as a simple parameter, a background against which quantum events unfold. This asymmetry between time and the other quantities in quantum mechanics has puzzled physicists for nearly a century. While we can ask where's the particle, and get an answer involving superposition and probability, we don't ask when is the particle, in the same way. Time, in standard quantum mechanics, is absolute and classical, not quantum mechanical. This treatment of time in quantum mechanics creates conceptual difficulties, especially when we try to combine quantum mechanics with general relativity. In general relativity, time is dynamical and relative. It can stretch and warp, flow at different rates in different places, and is intimately connected with space. But in quantum mechanics, time is a fixed background, uniform and universal. These two fundamental theories of physics, both extraordinarily successful in their own domains, treat time in completely incompatible ways. Reconciling them is one of the central challenges in the search for a theory of quantum gravity. One approach to quantum gravity, called the Wheeler-DeWitt equation formulated in the 1960s, suggests something even more radical. Perhaps at the deepest level of reality, time doesn't exist at all. When physicists try to write down an equation describing the quantum state of the entire universe, time disappears from the equation. The universe as a whole, according to this view, simply exists in a timeless state. All moments of time, past, present, and future, exist simultaneously in a timeless quantum superposition. What we experience as the flow of time might emerge only when we consider subsystems of the universe, only when we divide reality into observer and observed. This idea, sometimes called the timeless or frozen universe, is deeply strange and counterintuitive. If the universe as a whole is timeless, how does time emerge for us? Some physicists suggest that time is an emergent phenomenon, like temperature or pressure, not fundamental, but arising from the behavior of more fundamental timeless ingredients. Others propose that time is connected to entanglement, the quantum mechanical phenomenon where particles become correlated in ways that can't be described by considering them separately. As the universe evolves, quantum systems become increasingly entangled, and this growing web of entanglement might define the arrow of time. Another profound insight from modern physics concerns the relationship between time and information. In the 1970s, physicists studying black holes made a surprising discovery. Black holes have temperature and entropy, and they can actually evaporate over time through a process called Hawking radiation, named after Stephen Hawking, who discovered it. As a black hole evaporates, it radiates particles, slowly losing mass until eventually it disappears completely. This process takes an extraordinarily long time. A solar mass black hole would take about 10 years to evaporate, but it's a real physical process. The connection to information comes from a puzzle called the black hole information paradox. When matter falls into a black hole, it seems to carry information with it, information about the quantum state of the particles. If the black hole then evaporates completely, where does that information go? Does it disappear forever, violating quantum mechanics' principle that information is conserved? Or is the information somehow encoded in the Hawking radiation, preserved in a scrambled form? This paradox has driven decades of research and has led to deep insights about the nature of space-time, entropy, and time itself. Recent work suggests that the information is indeed preserved, encoded in subtle correlations in the Hawking radiation, but understanding exactly how requires thinking about space-time in new ways. Some physicists propose that the interior of a black hole and the radiation it emits are actually describing the same physics from different perspectives, a radical idea called black hole complementarity. Others suggest that spacetime itself might be emergent, not fundamental, arising from more basic quantum information. In these views, time, like space, might be an approximate, emergent concept that breaks down at the most fundamental level. The study of the very early universe also provides insights into the nature of time. In the first fraction of a second after the Big Bang, the universe was so hot and dense that quantum effects dominated even at cosmic scales. At the very earliest moments, the Planck time, about 10 superscript 3 seconds after the Big Bang, spacetime itself becomes quantum mechanical, and our usual concepts of time and causality may break down completely. We don't currently have a complete theory that describes this era, but various approaches to quantum gravity suggest that time itself might have had a beginning, not in the sense of a first moment in time, but in the sense that the dimension we call time might have emerged from a more fundamental timeless reality. Some cosmologists, including Stephen Hawking, proposed that in the very early universe, time might have behaved more like a dimension of space than like time as we know it. This idea, called the no-boundary proposal, suggests that if you could travel backward in time to the Big Bang, time would gradually become space-like, and the concept of before the Big Bang would become as meaningless as asking what's north of the North Pole. Time would have no boundary, no edge, no beginning in the usual sense. It would simply close smoothly like the surface of a sphere. Looking toward the far future rather than the distant past, physicists have traced the possible fates of time in our universe. If the universe continues to expand forever, as current observations suggest it will, entropy will continue to increase until the universe reaches a state of maximum entropy, the heat death we discussed earlier. In this far future, perhaps 10 superscript 1 years from now or beyond, all stars will have burned out, all black holes will have evaporated, and the universe will be a cold, dark, nearly empty expanse containing only a thin bath of radiation at a temperature barely above absolute zero. In such a universe, would time still have meaning? With no structure, no change, no events to mark the passage of time, the thermodynamic arrow would effectively disappear. Some physicists speculate that in the heat-death universe, time might become subjectively meaningless even if it continues objectively, like a clock ticking in an empty room with no one to observe it. Others suggest that rare quantum fluctuations might occasionally create temporary decreases in entropy, brief islands of order in the sea of maximum entropy, and that consciousness, if it could somehow exist in such a universe, might only arise during these fluctuations, creating temporary arrows of time pointing in random directions. And so our journey through time comes to its end, though the mysteries of time continue, unfolding in laboratories and observatories, in mathematical equations and philosophical contemplations. We've traveled from ancient sundials to Einstein's relativity, from Newton's absolute time to the block universe, from entropy's arrow to quantum mechanics' strange relationship with time. We've learned that time is far stranger than our everyday experience suggests. It's not absolute but relative, flowing at different rates depending on motion and gravity. It's not separate from space but woven together with it into four-dimensional space-time. It has a direction, an arrow pointing from past to future, driven by the increase of entropy from the universe's special low-entropy beginning. And at the deepest levels of reality, time itself might not be fundamental but emergent, arising from more basic timeless ingredients. We've discovered that the faster you move, the slower time passes for you. That clocks run slower in strong gravitational fields. That simultaneity is relative. Observers in different reference frames can disagree about whether events happen at the same time. That the past, present, and future might all exist equally in the block universe, with our sense of time's flow being a feature of consciousness rather than fundamental reality. We've explored how entropy defines time's arrow, how the universe began in a remarkably low entropy state and has been evolving toward higher entropy ever since. How our memories depend on entropy increase, how consciousness might require the thermodynamic arrow. How time-symmetric fundamental laws somehow give rise to the time-asymmetric world we experience. We've touched on the deepest mysteries, how to reconcile quantum mechanics with general relativity, whether time exists at the most fundamental level, what happened at the Big Bang and what will happen at heat death, whether information is truly preserved in black hole evaporation, whether time itself might have emerged from something more fundamental. But for all our scientific understanding, time remains in some sense ineffable, beyond complete comprehension. We know more about how time behaves than we did centuries ago, but what time actually is, its essential nature, remains elusive. Augustine's confession still resonates. We know what time is until we try to explain it, and then we find ourselves in deep waters. As you rest now, drifting towards sleep, you are moving through time in the most immediate and personal way. Time carries you from waking into sleep, from this moment into the next. You don't need to understand time to experience it, to live within its flow. The mysteries can wait. The equations can wait. The philosophical puzzles can remain unsolved. For now, there is only the gentle passage of moments, one flowing into another. You're breathing, steady and slow. Your heartbeat, marking time in its ancient rhythm. The quiet descent from consciousness into sleep, a daily journey you've made thousands of times, surrendering to time's current. You are a pattern in space-time, a world line curving through four-dimensional reality, a temporary arrangement of matter and energy that has existed for your entire life and will exist for all of it, timelessly present in the block universe even as you experience yourself moving through it moment by moment. Rest in that paradox now. You are both timeless and temporal, both static and flowing, both a complete curve in space-time and a consciousness experiencing time's passage instant by instant. You don't need to resolve the contradiction. It's enough to simply be, to exist in this moment, held gently by time's mysterious flow. The universe continues its evolution from low entropy to high, from the ordered Big Bang toward eventual heat death. But that process takes billions upon billions of years, unfolding on timescales so vast they're essentially eternal from your perspective. For tonight, the universe is stable, time is flowing gently forward, and you are safe in its current. Let go now of all the questions, all the theories, all the attempts to grasp what time is. Let yourself drift in time's flow, neither fighting it nor trying to understand it, simply allowing it to carry you from this moment into sleep, from wakefulness into dreams, from the known into the peaceful unknown. Time will continue without your attention. The laws of physics will keep operating. Entropy will keep increasing. The universe will keep evolving. And you can rest, can sleep, can surrender to time's gentle inexorable flow, knowing that time has carried you safely from birth until now and will carry you gently through the night into tomorrow. Sleep well, child of time. You are held in time's embrace, carried by time's current, safe in time's flow. Past, present, and future surround you, the block universe containing every moment of your life, timelessly present even as you experience them one by one. Rest now. Time flows on, patient and eternal, and you flow with it. Good night.